Welcome back to Pratik Academy. In last video, we have seen sample numericals based upon first chapter, and in this video, we are starting our second chapter, that is single degree of freedom system. Okay. As discussed in first chapter, single degree of freedom systems are the systems which require only one parameter to completely describe its state at any instant. Okay. In this chapter, we are studying damped vibrations of single degree of freedom systems. Okay. Then these damped vibrations are further classified into groups: free damped vibrations and forced damped vibrations. Free damped vibrations means there is no any external force, no any external force is acting on system while vibrating. Then vibrations are free vibrations. In case of forced vibration, there is a external force acting on body and makes it vibrating. There are three elements in damped vibrations or damped vibrating systems. One is a spring, okay, second one damper, and third one mass. So these are the basic elements in damped vibrating systems, in which damper is an element which absorbs energy or opposes movement of system and make it to rest. Okay. First, see what are the types of damping. So first type of damping is very simple one. It is viscous damping. Suppose there are two plates, plate 1 and plate 2, separated by thickness or distance t, and fluid is flowing through between them, or fluid is present in between them, having viscosity mu. Okay. Then according to Newton's law of viscosity, we have shear stress is equal to mu into du upon dy, that is change in velocity per unit change in height or thickness. So here we have tau is equal to mu v upon t. So this is the shear stress. To find out shear force, we have to multiply by it by area A. Then our equation becomes shear force is equal to mu a area upon t into velocity v. Okay. So this shear force is opposes movement of this velocity, movement of this plate. Okay. And for given system, mu or fluid is constant, so viscosity is constant, area is constant, and thickness is constant for given dimensions. So this resisting force is proportional to velocity. Okay. It means viscous force or resisting force is linearly proportional to velocity. An example of this type of damping system is fluid dashpot system. Okay. As these systems, in these systems, resisting force or damping force is linearly proportional to velocity, so these systems are mostly preferred while modeling of any vibrating system. Okay. So this constant, this proportionality sign, if we replace by constant, and we take equation becomes F is equal to C x dot, where C is called as a damping coefficient and its unit is Newton second per meter. Okay. This damping coefficient of this damping coefficient is depending upon two parameters. First is the viscosity of fluid, then second one dimensions of system, that is dimensions of damper. As this, if we draw graph of resisting force with respect to velocity, then as it is F is linearly proportional to velocity, so this graph is straight line. Okay. Straight line. So this is the first type of damping. Now second type of damping is called eddy current damping. So it is based upon principle that when a non-magnetic sorry when a non-ferrous conducting object, for example copper plate or material is copper, say, when a non-ferrous conducting object is moved in a direction perpendicular, important is perpendicular to line of magnetic flux or field produced by permanent magnet, then as object moves, current develops inside the object. Current is developed inside the object which is proportional, again, which is proportional to relative movement, and this eddy current develops its own magnetic field and which opposes movement of object. That means suppose there is a permanent magnet having, or there is a magnetic field and as produced by permanent magnet, and if we move one object, that is non-ferrous conducting object, through this, then magnetic field is developed within this object due to eddy current and which opposes its further movement. Okay, so this is eddy current damping. Then next is a dry friction damping or Coulomb damping. This damping is due to friction between two relatively moving objects which are unlubricated. Okay, which are unlubricated. That means there is no any fluid layer present between them. So if we draw graph between coefficient of friction versus velocity, then if surface is ideally smooth, then coefficient of viscosity or coefficient of friction remains same or independent upon velocity, it remains constant. Okay, for smooth surfaces. Okay, if surface is irregular, then with increasing velocity, initially mu or value of coefficient of friction decreases and then remains constant. So for this is for rough surfaces, and if the surface, if these two surfaces are separated by fluid layer, then as discussed in last, with increasing velocity, mu value, that is coefficient of viscosity here, is also increases for viscous damping case. Okay, now we know that force, that is the resisting force, frictional force, is equal to coefficient of friction into normal direction. This normal direction will be equal to weight of body if surface is horizontal, or if it is inclined, then normal direction developed by surface. As it is constant for given system, then the force will also behave or gives same nature. Frictional force is also giving same nature as that of mu with changing velocity. Okay. So this is the second type of damping, dry friction or Coulomb damping. Then next type is solid or structural damping. This is due to internal friction of molecules. Okay, this damping is due to internal friction of molecules. Some energy is utilized against this friction and thus energy of system is reduced. It is very small. Okay, this damping is of very small amount. When materials are deformed, energy is absorbed in form of strain energy in that deformed objects and from steam, and this energy is released to surrounding in form of heat. Okay, so energy from steam is absorbed first in elements, deformed elements, and released due to internal friction of molecules to surrounding. So energy is lost from surrounding, and by continuous absorbing or and releasing energy to system, finally our system comes to rest. Okay. When such body vibrates, then stress strain diagram forms a hysteresis loop. It is, if we draw stress versus strain diagram for such a compounds or substances, then they form a loop. This loop is called as a hysteresis loop. Okay, then this is while loading condition, this is while unloading condition. In this area under the loop represents energy lost by system while vibrating. Okay, then next type of damping is non-linear sleep or interfacial damping. Okay, this is again microscopic sleep between machine joint. Okay, this damping is present, or this damping is due to slip between machine joint when they are acted upon by fluctuating loads. Okay, when machine is acting upon by fluctuating loads, then due to slip between machine joints there is a damping, and the damping is called non-linear slip or interfacial damping. This damping depends upon first surface roughness of contact parts, then pressure exerted at the contact, and amplitude of vibrations. Okay, this damping depends upon surface roughness, second pressure, and amplitude of vibration. Okay, if we draw graph of energy lost in damping versus this contact pressure, then this graph is forming this nature. Again, for low amplitude condition or small amplitude situations, if we increase amplitude, then same nature is observed but having higher peak values. So this is for large amplitude conditions. Okay, that means initially with increasing pressure, amount of energy lost is increases and then again decreases. So there is one optimum value of contact pressure at which damping is maximum. Okay, so these are the types of damping. So we have discussed types of damping as first is a viscous damping. Viscous damping is very simple one, and nature is it is linearly proportional to velocity of fluid. And second one we have discussed, it is eddy current damping, is due to development of eddy current in non-ferrous magnetic material. Then third one is dry friction damping. It is due to friction between two moving parts, then it absorbs energy and makes system to rest. Then next one was the next part. So next is solid or structural damping. This is due to internal friction of molecules and it is very small amount. Okay, in this area represents energy lost due to this damping. Then non-linear or slip damping, non-linear slip or interfacial damping, this is between machine parts due to fluctuating loads. This depends upon surface roughness, pressure, and amplitude of vibrations, and there is one optimum value of pressure at which energy lost is maximum. So in this video we have seen types of damping. If you like this video, please comment, share this video with your friends, and subscribe our channel. Thank you.